All right, so this is the second exam review session. There's a bit fewer people here. That's okay. I've sent out this document here that we see in the notebook, and it has a fair amount of exercises for us to look for. They're pulled from various texts, various resources, okay, everything like that. Most of them have been modeled after things that you have definitely seen before, no curveballs, okay? And some I definitely do give you some hints to think about. Now, calculus 2 is a very dense subject, and I'm familiar with that. Okay, as someone that's been doing this for 12 years, I know very well that this is dense. So, what should we think about when we go into the exam setting? And that's what I want you to think about in this, like I put in the first page. And definitely this part here. The goal is to understand the how, not just the what. It is not enough to just get the answer. But what matters is the solution path. Okay, those of you that have seen me before, you guys know, okay, even if you see me for like Calc 1 or even pre-calc, okay, it's all about the solution path, okay? How do you get to your answer? And it's about the logic. And so we ask ourselves, what formulas can I use? What results? What theorem can I use? What should I use? Why can I use it? Okay, remember, for example, the integral test, it's a pain in the butt to use. It's not just, oh, take the integral, I'm done. No, you have to verify that your helper function is positive and decreasing, and then you can take the integral. It's not just enough to take an integral. Okay, so you have to make sure that you know what you're doing. How can I move logically from one step to the next? Folks, mathematics is about logic. It is about logic. It is about the line of reasoning. And I feel like a lot of people lose sight of that. It's not just turn to crank, get an answer, memorize a process. That is definitely not what that is. I can tell you there have been some integrals, some derivatives even, that I had to look up this semester for one of my classes because I forgot how to do them. I forgot how to do integration by parts. I forgot how to take, partial derivatives. I forget things all the time. That's why this exam formula sheet here that we've been using for the past year, folks, I think it's going to be your valuable study tool. Have this in front of you when you study. Have your notes in front of you when you study, okay? Don't try to pull things out of thin air. Don't try to reduce it to a Quizlet. Also ask yourself, are there multiple ways to solve the problem? Okay? Sometimes there are multiple ways to solve the problem. That's what mathematics is about. If I remember right, there are at least like 5 ways to prove there are infinitely many primes. Same problem, different solution. Like, for example, if I tell you to write code to estimate an integral, I'll probably get like, how many people do we have here? Like 20? I'll get 20 different responses. That's the beauty of it. Now, what I think is the most important here, that last bullet point, does my work flow? I see too many treasure maps and no treasure. Now, there is a treasure map, but maybe a boxed answer, but I have to follow this thing all the way around, okay? Make your grader happy, okay? Left to right, top down. Each line is a step, okay? The less that we have to decipher what you didn't put on the paper, the better. Have your workflow. Use your scratch paper if you're allowed on your exam, okay? And transfer the most important stuff onto that exam paper. Take this not just for this class, but if you attempt any other math classes, linear algebra, differential equations, probability theory, measure theory, okay? Graph theory, heck, even discrete mathematics, combinatorics, okay? Take that reasoning with you. And folks, with that, I really wanted to go ahead and start with our first problem, literally the first problem in this set. I didn't realize that these consoles get warm. I think it's, yeah, okay. Here we go. We're going to start off with some techniques of integration. We're going to start off here with what I think is a fairly easy one. X cubed sine 2x. Let's think about our techniques of integration. What was the first brand new integration technique that we learned? The first brand new one. That's technically an old one. That's technically an old one. Integration by parts, or as I say it, IBP is supreme. But when do we use IBP? Products of functions. Products of functions give you a clue. In particular, products of that type give you it. So let's briefly review what IBP is, integration by parts. That's not what I want. All right. IBP is supreme, y'all. If I want to integrate UdV, then I look at UV minus the integral of V du. The integration by parts formula, the classical formula. Do we still need to know it? Yes, we do. This is just the product rule backwards. Further, if you have a definite integral, you have the evaluation on the boundary for UV, okay? So we have UV evaluated on the boundary minus the integral from A to B of V du. Okay, definite integrals, same thing. So why am I talking about integration by parts? Because this thing right here lends itself very well. We have a heuristic, okay? 5 letters sounds like a nice coffee drink. What's the heuristic that we think about for integration by parts? 5 letters. Liate. Liate, okay? I'll have a vanilla liate, please. Actually, if someone wants to get me one, that would be great. No, I'm kidding. But what do each of these letters stand for? Algebraic function, right? Trig and exponentials. They're very good. When we think about this from the top down, that tells us how to select our U. That's a terrible looking U. When we look at this from the bottom up, can everybody see that thing on the right, the bright green arrow? Okay, if the color doesn't show up well on the projector, please let me know. The thing going from the bottom up, that's how we select our DV. And this is sometimes, you can also think about this as called detail. D, and then if you spell liate backwards, it's detail. How do you want to think about it? All right, so let's ask this question. What here in my integrand, what should I select as my U? What should I select as my DV? What should I select as U and what should I select as DV? X cubed for U, very good. And there you go. You fill in U and DV. Then you fill in your table with your nice university-sponsored colors. Du, think about this. U to du is a derivative. And the derivative of x cubed is 3x squared. Then we have dx because of the differential. And then the antiderivative of sine of 2x, what is that? Okay, say that again. No, not quite. Yes. That's almost a derivative. It's not negative 2 times sine x, but it's negative 1/2. Okay, this is a very good thing here. Okay, so think about this. Antiderivative of sine is negative cosine because the derivative of negative cosine is a positive sign. But where does that 2 come from? That's just the chain rule. Okay, think about this in terms of a basic U substitution. Okay. And then, folks, what you have here, you just follow your path. UV minus the integral of V du. So this integral now reduces to minus 1/2 x cubed cosine 2x minus the integral of V du. That's not good looking too. Cosine, right? Yeah. Yes, I can pull the negative 3/2 out. Okay. I can do that. But now take a look here. That resulting integrand lends itself to doing by parts again. So if I do parts again, I need to make similar looking choices, okay? Which I'll just write that down here. If I make similar looking choices here, I want U equals x squared, and then dv equals cosine of 2x dx. Okay, fill in the rest of the table. Oops, that should be a plus sign. Okay. And follow your path. And then you keep doing this until you get something that is manageable that you know how to do this. Okay. You'll have to do this in this case 3 times. Now, this was with the classical formulation, and I really stress that you should know this classical formulation of integration by parts. This formula up here. We have all the shortcuts in the world. But why have a shortcut if we don't know how to get there in the first place? That's the biggest thing, okay? Keep this in your back pocket. Now, there is a nice way to handle this. How many of you have seen the movie Stand and Deliver? Watch that movie. It's one of my favorite math movies. Okay? Now, in that movie, it's in passing. It's just really a background object. But they're doing an integration by parts integral. And they do it in this way, tabular integration. As Black Pen, Red Pen calls it, like, comment, and subscribe, the DI method. Sound familiar? Now, we're going to make a table here. I have a D column and an I column. The D column is going to be all my U stuff. And the I column is going to be all my DV stuff. With me? Now, we selected U at the starts, okay, as x cubed, and I as sine of 2x. Okay? So that's the first step. That's how you initialize this. You make your initial choices of U and dV. Now you're going to take the derivative on the D column until the derivative is 0, until it vanishes. And with a bunch of stuff from the power rule, factorials really, okay? We get that. And then we're going to integrate the same number of times in the I column. Okay, so we go ahead and write this. Okay, note that each step here we're going to divide because we're integrating. Okay, we got to be careful here. Antiderivative of sine is negative cosine, but I already have a minus, so that's going to be a plus 1/8. And I have a 1/16 here. Now this is where the magic comes in. This is where the magic comes in, and then this is how you can convince yourself that you have the ganas to do this integral. What we're going to do is along the side, I'm going to go ahead and make a list of alternating signs. Plus, minus, plus, minus, plus, just all the way down. And then 3 little words here. Tick, tack, toe. I'm going to join the first thing in the D column to the second thing in the I column, the second thing in the D column to the third thing in the I column, and I repeat with the shoelace pattern until I've exhausted everything. And each of those shoelaces is a product, and we give it the corresponding sign. So, with this information, I can very quickly tell you that the antiderivative that we seek, x cubed sine 2x, the antiderivative we seek here, okay, we're going to have x cubed times negative 1/2 cosine 2x, but then we have a plus sign. So plus times minus is positive times negative is a negative. So we'll have a negative 1/2 x cubed cosine 2x. Next term gets a minus. Minus 3x squared times negative 1/4 sine 2x. Negative times the negative is a positive. So we get a plus sign there. And you see that we just followed through with this checkerboard pattern. Okay. The next one's going to be a plus 6/8. I'll just write it like that. Cosine 2x. And then minus 6/16 sine 2x plus a constant. Now, when can you use this table method? Polynomial type thing against exponential, sine, or cosine. That's the beauty of the table method. That's the beauty of the table method. Polynomials against sines, cosines, or exponentials. So you have like x against e to the x, cosine of x, sine x, table method right away. You get it. Bing, bang, boom, you're done. Are there any questions so far? No questions so far? If there is, please, yes. Yes, everything will be released as soon as I get home much later tonight. So you'll have to, I'll be very tired. Yes. Say that one more time.
Like, what makes this possible?
A polynomial. Yeah, so table, okay, so I'll make this as a remark here. Okay, use table, use DI if you have a polynomial against an exponential. That funky little thing in the exponent, by the way, is a lambda, okay, e to the lambda x. Okay, polynomial against cosine of x, cosine, or polynomial against sine. Okay, and this is for saying that P a polynomial. Why? Because the derivative of a polynomial will vanish. Now, if you have like a square root t in there, forget about it. You can probably do some priming substitution to get rid of it, but just a straight up polynomial against sine, cosine, or exponential, just like these three. Okay. Good question. Very good question. Correct. But it is still good to know the classical formulation because of this. Or even better, because I did this one in the last session. Something like this. Okay. Let's think about what's available here. We have x to the fourth log x. I can generalize this for x to the p log x for any p. I'll leave that as an exercise for y'all, but let's think about this, okay? Lyotte. Remember, top down, the Lyotte heuristic tells me what to select as my u. So u is log. If I take the derivative of log, will it eventually vanish? Will it be 0? No. Log x, 1 over x minus 1 over x squared, 2 over x cubed, minus 6 over x to the fourth. Hey, does that sound like the Taylor series exercise you've done for that one? Yeah. It doesn't vanish. So DI is not a very good way to like knock this out immediately, but it can still help you organize the information. Okay, it's not a shortcut, but a shorthand. Not a shortcut, but a shorthand. It still points to the same information, okay? For you folks that know how to use pointers in C++. Heck, it even is a pointer anyway. Who knows how to work in C++? Who works in Java anyway? Python supremacy. Okay. So we're going to go ahead and do, as we mentioned here, u equals log x, and dv is x to the fourth dx. Okay. Get the other rowdy colors in here. So du is 1 over x dx. And then, why did I write that? Okay. Then dv is this. And then we follow our path. uv, 1/5 x to the fifth log x. Okay, let's write it here. The integral of x to the fourth log x dx is u times v 1/5 x to the fifth log x minus the integral of v du. Folks, what happens to that x to the fifth into 1 over x? Say that one more time. Exactly. Okay, we have a common factor that we can banish here. Okay, so that last part there just reduces to this. And folks, now it's just a power rule exercise. Now it's just a power rule exercise. The extra 5 came from dividing by 5. 5 times 5 is 25. So again, while the table method is helpful, okay, it doesn't solve all your problems. Okay, it's a shortcut, not a shortcut, but a shorthand in some cases. Yes, this is why it's so good to know the classical formulation here. Any questions? Okay. I want to look at this next one here. Number 1-4, and then I'm only going to give you like the hints because sorry, yes. Okay. Exponent rules. Exponent rules, that's just a basic thing, right? When we divide with exponents, we subtract powers. 5 minus 1 is 4. Okay. Still a good question. Okay, any others before I move on? Take a look at this integral. Integrating cosine of square root of x. How will have you guys think about that? All right, so I want to integrate this thing, but it doesn't look really friendly, right? Wouldn't it be nice if that square root wasn't there? Then we'd be done, right? Antiderivative of cosine x is sine x. We'd be done, move on. But we know that's not how this works out, right? I just don't write sine of square root of x and move on. That's certainly false. Okay, think about it because of the chain rule. Okay. If I take the derivative of sine square root of x, yeah, I get cosine square root of x, but I gotta multiply by the derivative of the inside. We don't have that stuff here. And so how can we attack this? And the answer is we just go ahead and try to get rid of the square root. How do we get rid of square roots, by the way? We square stuff, right? So wouldn't it be nice if I could just square and be fine? We're gonna do what I call a priming substitution here, okay? I'm gonna prime this with the substitution t equals x squared, which basically says x equals square root t. Wait, no, I'm sorry. I have this backwards. T is equal to the square root of x, which means that x is equal to t squared. Okay. Now I'm going to go ahead and use the pair on the right. Okay, this is going to make my life a little easier because remember, when I change variables, I'm going to change those differentials. Okay, I'm in a sense changing measure. Anyway, so remember when we do a u substitution, but that's not a u, Sean. I know. It's called u substitution because it's the first letter that we think of. You can use whatever letter you want. X, Y, Z, UVW, ST, whatever. So here I'm going to do x equals t squared. So dx is equal to what? Dx is equal to what here? What's the derivative of t squared? 2t dt. You need that differential there. 2t dt. Okay. Now we just toss stuff in. And folks, there's a reason that we did this, okay? Cosine of square root of x. Square root of x is t. So this is now the cosine of t. Dx is 2t dt. And folks, do you see how we have our dx earmuffs here, right? Now what integration technique can they use? Say that again. IBP. We're using parts here. This is a polynomial against a trig function, a sine or cosine. That's what we did that priming substitution. So we go through it, get the priming substitution, and then remember at the end, because your original problem was an x, your answer should be an x. So you have to back sub here. You got to use that guy there. Okay. When you do that, in fact, let's just show you how powerful this thing is. 2t, 2, 0, cosine of t, sine t with a minus, no, with a plus sign there, then a minus cosine, tic-tac-toe. Okay, what do we get here? 2t sine t And then minus times minus plus. So we get a plus 2 cosine of c plus a constant. And now I back sub. Okay. 2 squared x, that's a bad 2. To me, I think this is the most straightforward way of solving this problem. I think when you all encountered this in your homework set, you just had to do parts directly by choosing u equals, I think, yeah, u equals cosine squared x as your u, and then dv is dx. You can do that, but I think the more natural way is to do a priming substitution, okay? Showing you how to use these techniques in tandem. Ain't it fun? Any questions on this? Okay, I'll let you absorb this for a little bit. Say that one more time. Okay, you kind of trail off there. So well, the thing is here, 2t does not rely on 2x here. Okay, remember that here we have dx equals 2t dt, and that's why I circled those two terms in blue, because those are our dx earmuffs. That whole thing together is dx. Cosine of t, that's cosine of square root of x, and we changed the variables there, right? Okay, with variable substitutions, you don't need all the pieces there, but you need most of the pieces. Okay, here I'm pushing forward. This is an example of what's called a push forward, or anything could be called a push forward, but this is an example of kind of substitute where we're pushing forward from x to t. Okay, I'm basically expanding it into something so I can use something else. Because as it stands, that original integrand, I don't really have anything to work with. Okay. Again, you just have to plug in as you go, right? Cosine of square root of x. Well, square root of x is t. Okay, I have that. Dx is 2t dt. I just replaced dx with 2t dt. Does that answer your question? Okay. Good questions, folks. Good questions. Any other questions? Yes. Right. So the alternative solution here, the alternate solution, you guys did this with like, I think sine of log x and cosine of log x. I think as well with that one, I would have done like x equals e to the y, and then everything works out beautifully. So the alternate solution, here more one way to solve the problem. If we set u equals just cosine of square root of x and dv equals dx, then v is equal to x, but then what is du? Again, you got to use this chain rule stuff. Minus sine square root of x times the derivative of the inside, which is 1 over 2 square root of x. Okay, and now take a look at what happens here. We'll have x, let's see, x cosine square root of x minus the integral of v du, and that kind of looks a little more complicated. But I think if I remember what happens here is you have to like loop back. Okay, so remember when you integrated like say exponentials against sines and cosines, e to the ax cosine bx type of things, those integrals show up a lot in Laplace and Fourier transforms for you electrical engineers here. You have to like loop back and solve for the unknown integrand. Okay, that's an example of what happens here. If you start with this one, you'll have that solution there. It's also a good exercise to attack it there to verify that you get the same one. Again, this priming substitution, I think, is just like the more natural way to do it. I think it would be nice if that thing wasn't there. Undo it somehow. Boom. Speaking of trig, 1.6. I want to integrate sine squared of 3x. At the start, a lot of you would have been tempted to use the power rule here. Not a bad choice, but sadly it doesn't work out. Remember, you can verify your antiderivative by taking a derivative. Okay. Probably sit down. Maybe I can. So look at the hint there. I tell you to use the so-called power reducing or half angle, or depending on the instructor that you have, he calls this the golden identity. Okay, sound familiar? Now the question is, what identity is that? What identity am I really talking about? Say that again. Almost. You're almost there. You're almost there. There you go. So I'm going to write it like this here, okay? Ooh, setting is much more comfortable. Why didn't I do this earlier? So we're going to be able to rewrite the sine square of whatever, sine square of u, as 1/2 of 1 plus 1 minus. See, this is why you study with your formula sheets in front of you, because I don't remember this identity half the time. 1 minus cosine 2u. Half the value, double the angle. Say that again. Half the value, double the angle. Okay? The angle gets doubled. And so instead of a 3x, what am I going to have as the angle and the cosine? The 6x. So we're going to go ahead and use this power reduction formula, the half angle formula, the golden identity. Okay? So we have the integral of sine squared 3x is equal to half of 1 minus cosine of twice the angle, so cosine of 6x. And now I have a linear combination of two extremely easy integrals. Now, when I multiply it through, okay, or I just ignore the 1/2, okay, well, when I do that, okay, what's the integral of 1/2? The antiderivative of 1/2. What's the antiderivative of 1/2, anybody? One half x. Okay, so remember, you have to expand this thing, or you can push out the 1/2 and deal with it later. That's fine. So if I do this, that should be a minus. Okay. Antiderivative. Oh, sorry, I already did the thing ahead. Okay. So antiderivative of 1/2 is just 1/2 x. And then I have 1/2 times the antiderivative of cosine 6x. What's the antiderivative of cosine? Antiderivative. The antiderivative of cosine x. That's sine x. Okay, remember the directions that you're going, right? Derivative of sine is cosine. Derivative of cosine is negative sine. Antiderivative of cosine is a plus sine. So I'm going to have a sine of 6x here. But what else do I need here? What else do I need? Well, yeah, I'm going to need a plus c. But that derivative, that thing in the inside of the parentheses is incomplete. If we were taking the derivative. So if we were taking the derivative, let's actually think about this as an exercise, right? Derivative of sine of 6x. Derivative of sine is cosine, as we said. And then the chain rule says that we pass the derivative operator into the next link in the chain, which is 6x. We multiply by 6. But integration is an inverse operator of differentiation. So instead of multiplying, I'm dividing. Folks, the pro tip here is this. Whenever you have a linear function composed and you're doing a u substitution, think about the antiderivative of the outside function, and then you divide by the slope of the linear function. The slope there is 6. And folks, that's it. That's all you got there. Are we clear on that process there? Are there any questions at all? Please feel free. Yes. Yeah, so the mnemonic I have is crud. So I say half the value That's this 1/2 here. And then double the angle. Half the value, double the angle. Now, when you integrate trig stuff, okay, if you have just even powers, you're going to have to use these reduction formulas, okay? And then, of course, some binomial nonsense if you have to, like this is sine to the 4th. Remember that exercise? Sine to the 4th and write it in terms of cosines. Yeah, you guys know what I'm talking about, okay? There are more than one, like if you just see sine squared, don't just write it as 1 minus cosine squared, because guess what? You still have to integrate cosine squared. You use that formula. Let's actually look at 1/7, okay? Before we do, any other questions on this one before I turn the page? 1/7. Sine cubed cosine x squared x. Okay. I have 3 sines and I have 2 cosines. A bunch of stuff is here, okay? Now, you might be thinking, well, I'll just write cosine square as 1/2 of 1 plus cosine 2x. That doesn't really do you any good. Because now you got to worry about this product of sum identity, which we don't worry about here. So what do we think about? These functions, these sines and cosines, and then as we'll see, secants and tangents and the like, those functions, like ogres and onions, have layers. See, a lot of you are too young to remember Shrek. Got it on DVD back in like what, 2001? You don't even know what DVDs are. So I want to peel away some stuff. The trick for these, when you have sines and cosines, you want to peel away 1. So we're going to peel. Okay? The key move is to peel it away. See, that's a joke. So we have sine cubed x, cosine squared x, dx equals, I'm going to peel away one of the signs. So sine x, sine square x, then times cosine square x dx. Okay, now what I'm going to do, because ultimately here I want to force a u substitution. Do you see how I have the 2 sines left over? What's the other way to rewrite sine squared? What's the more natural way to rewrite it? Everyone just lit up at that. That just made me so happy. Sine squared is 1 minus cosine squared. So I'm going to go ahead and color that in here. This thing here, we're going to just rewrite it as, so we have sine of x, and then we have 1 minus cosine squared of x. Okay, that's this thing right here. Okay, the 2 green things are the same. And then we have the other cosine, cosine square x. Now, why did I say I wanted to force a u substitution? Or some variable change, right? What would the variable change be here? Bing pots. No Brooklyn Nine-Nine fans in here? Okay. Wow, I'm turning into my leadership professor. He's like, you don't like humor, you don't like, okay. U equals cosine x. So what is du here? You just redeemed yourself. Caught your own rebound. Minus sine x dx. The derivative of cosine is a negative sine, okay? So you got to watch your sines, your sines, and your sines, your signs, okay? Do I have a negative sign in my integrand? Do we have a negative sign in my integrand? No. We just multiplied by -1. So minus du is sine x dx, and we've played for the match. And folks, take a look at this. Okay, take a look here. We've got sine x dx. I'll go ahead and circle that there. Sine x. Ugh. Where is undo here? Sine x dx. That's all minus du. Okay. And then the rest will have the following. Okay. So 1 minus cosine square x, that's 1 minus u squared times u squared du with a minus sign. Okay, let's pause here, okay? Does everybody see how I made those transformations? Are we okay with the transformations? Yeah, give me a thumbs up if we do. See, this is how you can tell I was a high school teacher. Okay. How do we handle this? Say that one more time. Yes, exactly. We multiply through, and you have the power to rule with the power rule. And then you back substitute, and then you're done. That's the punchline for this one. Any other questions on this one? Any other questions? All right, let's go ahead and take a look at 1.8 here. Now, instead of sines and cosines, we got secants and tangents. All right, I'll have you all think about this one here for a second. So for secants and tangents, the game is similar but slightly different, okay? Instead of with secants and sines and cosines, we're peeling away one. With secants and tangents, you want pairs. Pop quiz. What's the derivative of tangent? Let's try that again. What's the derivative of tangent? There you go. That one actually hopefully picked up on the mic. And loud and clear, everyone, what is the derivative of secant? Secant x, tangent x. Now that's when you say that with confidence, right? But hey, that's good, right? Strong and wrong, okay? That way we correct the mistakes now, okay? So let's just get those here on the screen so that those at home can see. The derivative of secant x is secant x tangent x. And the derivative of tangent x is secant squared. Okay? Those two facts will help you. Now, do you kind of see why we want to like try to peel away one? We want pairs of something, either a pair of secants or a secant and a tangent pair. So we're going to be using that, but we're also going to be using another identity. Is there an identity that relates the secant and the tangent together? What is that identity, my friend? This is going to be your best friend here. All right. Like I said, the game for secants and tangents is I want to go ahead and peel pairs. Okay, I want to get some pairs. Let's take a look here. I have an even number of both secants and tangents. I got 4 secants and I got 2 tangents. Okay. So we got to ask ourselves, how do I handle that? Well, I'm going to go ahead and separate a pair of secants. So we have this integral. And I'm going to separate a pair of secants. Okay. It's not secant, it's secan. Sorry, I had to do that. You got to make this fun somehow, right? Okay, so you can see this, right? Okay, we're going to peel away a pair of secants. Why? Because I'm going to use that identity that we just wrote up there, okay? In this yellow, we're going to have 1 plus tangent squared x equals secant squared x. But Sean, that says y. It's a dummy variable, right? You know, in VS Code, you just highlight over it and change the name of it. I got bullied into using VS Code, so yeah. Anyway. So we're going to use that, and I can do that on one of the pairs of secants. So we have the integral of secant square x times 1 plus tangent square x times tangent square x dx. And once again, there's that move that we just made. All right. Any suggestions on what to do next? Oh, you're very close. You are very close. U is just tangent, not tangent squared. Why? Because take a look at what I got. The derivative of tangent is secant squared. I got secant squared x dx just floating out there, right? In this color, u equals tangent x. Du is secant square x dx. Okay. What was I gonna do? Right. Secant square x dx. Those are our du earmuffs. Okay. You guys see why they're called earmuffs, right? DU headphones if you want to, okay? Best brand out there. That would be a great business idea, right? Anyway, we go ahead and fill in the stuff. So secant squared x dx is du, and I have u squared times 1 plus u squared du, and what do? Just like before. In fact, isn't this the exact same one that we got before? Oh, no, we had a minus there, but it's basically the same kind of thing. I trust you all can do that. Okay, are we good so far? Any questions on this one? Any at all? Okay. All right. So why did I have to talk about these? Because you might have, for example, a problem like here in 110. Oh, yes, sorry. That would be if you have an odd number of both secants and tangents. So if you have an odd number of secants and an odd number of tangents, you have to save one because then you get the secant tangent pair, and then the variable change that will make it secant. Now, again, for that one, you have to be a little careful. So, like for example, if I had like say 1 plus tangent squared, all that to like say cubed, then you have to expand that out very carefully using the binomial theorem. Okay, so or use the F word a few times. Not that F word. Okay, come on now. It's okay to laugh, guys. Okay. So yeah, so if you have an odd number of both secants and tangents, you want to save a pair. You want to save one of each. If I remember right, it's if at least one of them is odd, if I remember. So if you have like 5 here, this one, if I had 5 secants, then I pull out a secant. I have secant to the 4th, tangent squared x. And yes, yeah, then I would have make the change u equals secant x, I believe. Okay, and all that can be found in, let's see, that's going to be 3.2 part 2, secants and tangents. Just a plug for my own video there. Okay, use the offer. No, we're not doing a sponsor plug here. Let's do 110 here, okay? Because those integrals arise in these here. But however, read the instructions, okay? The instructions I gave you. By using an appropriate trigonometric substitution, evaluate the integral of x times square root x squared plus 16 dx. Now, this is also the important part here. I want you all to look at this very carefully. It's so important. I'm not highlighting it in yellow. I'm instead highlighting it in red. The final answer should not include expressions such as sine of arctan x or arc cosine of sine x. But whoever does, let me do it. No, guys. These are kind of messy. And you can always denest. And how do you denest? You use the strongest shape that is out there. The triangle. Draw your reference triangle. We'll get there. Now, it says by using an appropriate trig substitution. Anybody have an idea how else I could possibly evaluate this integral? What else could I do? How else could I have evaluated this integral if I wasn't using a trig sub? Yes. Sorry, say that again.
Like using the inverse and with one over x times.
No, I think you got a couple of things mixed up there. That's exactly what I was looking for. You could do this with a U substitution easily and you'll be done. But I want to demonstrate that sometimes there are multiple ways to attack an integral. We're going to attack this using trig substitutions. Okay, there was a problem in the homework set that was like this. It was like x cubed over square root of 1 plus x squared, I think. You had to do like an x times x squared thing. Now, speaking of which, what trig sub should I use? Any ideas? Let me remind you of an identity here. We actually just talked about this identity. Okay, we have 1 plus tangent square y equals secant square y. Does that almost look like the stuff in the square root? Number plus something squared? And this is the key. A lot of people have always asked me, I remember some of you all did ask me this question. How do I know what substitution to use? If you know your Pythagorean identities, if you know those identities, they motivate you to the substitution to use. Because folks, take a look here. I'll just tell you straight away, in this position, the winning move is to set x equals 4 tangent t. Why is that the winning move? This is such a powerful thing. Well, first off, before we do that, if x is equal to 4 tangent t, what is dx? Derivative of tangent? Secant squared. So 4 secant square x, secant square t dt. Now, the thing is, why is this so powerful? Let's take a look at the stuff inside the square root, okay? Let's take a look at that stuff inside the square root. We have x squared plus 16. We're replacing x with 4 tangent t. Let me fix that there. Now we use our exponent rules, right? I have the square of a product. That's the product of squares. 16 tangent square t plus 16. What can I do? Not quite yet. Yep, GCF, y'all. Common factor is 16, because what do you see? What's 1 plus tangent squared? What's 1 plus tangent squared? Secant squared. It's right there, right? That's why I mentioned that identity. So the stuff under the square root is just this. And now, when we take the square roots, square root of 16 is 4. Square root of secant squared just gives me a secant t. Now, folks, I want to make sure that we are very clear about one thing, and it is something that, like, I remember harping on a lot of you about this when we were talking about, like, arc length earlier in the semester. The square root of x plus y is not the same as the square root of x plus the square root of y. Do not do this. Do not do that. Because if we had that, we wouldn't even have Pythagoras in the first place. Are we clear? Go through this construction first, okay? Manipulate the stuff inside the square root. Then you manipulate it to something nicer. And now you just go. All right, now we're going to go ahead and substitute everything into the integral. Okay, we have x times the square root of x squared plus 16 dx. I'm going to use some colors here, okay? In green, in this green here, I'm going to use x equals 4 tangent t. In light blue, I'm going to do the dx bit. And finally, in orange, I'm going to have all that stuff inside the square root. With me? Okay, so I'm going to go ahead and replace with the colors. So the integral of x is 4 tangent t times the square root of x squared plus 16. Okay, we determine that that square root is equal to 4 secant t. And then finally, dx equals 4 secant squared t dt. Isn't it nice? Are you with me so far? You see how I got all those things? Yes? If the answer is no, please tell me. I'm glad. I'm happy to explain it. Okay. We'll multiply all those fours together. I believe that gives us 64. 4 cubed. 4 times 4 is 16. 16 times 4 is 64. Yeah. Okay, and the good news is we kind of already have like our separation already done here. What like we were talking earlier with the secants. So we have 64, Nintendo 64 times the integral of tangent t secant t secant squared t dt. And I want to go ahead and make the variable change. U equals secant t. Because what's the derivative of secant? There you go. And folks, you see how that works out, right? So I'm not going to write down what comes out of the substitution because it'll basically just be a u squared that we're integrating. And how do we integrate u squared? U cubed over 3, right? Power rule. So I'm going to go ahead and save that. We're going to do the following. We have 64, and it'll be times 1/3 of u cubed. U is secant t. So we have secant cubed t plus a constant. Okay, so that integral on the line above just reduces to basically u squared du. Follow? Okay. But am I done? No. No. We're not done yet. We have to put this back in terms of x. So we take our original substitution, which I'm going to cleverly do this here. We're going to take our original substitution, and we're going to use that to draw our reference triangle. So to do that, we go ahead and take our original substitution, x equals 4 tangent t, and we solve for the trig function. So how do I solve for the trig function? How do I get the trig function by itself? Not quite. We're not there yet. How do I get the trig function by itself? How do I just get tangent t equals something? Divide by 4. That's the thing. So we have x over 4 equals tangent t. But why did I want to do that? Use the triangle. Now, if you take the arctan of both sides here, you get t equals arctan x over 4 and plug it in there. That violates the instructions. I want you all to try to get this into a nice way as possible, okay? So the way we do this, we have x over 4 equals tangent t, and those 9 letters, SOHCAHTOA. We draw the triangle. Tangent is what part of the triangle over what part of the triangle? There you go. Mark your angle. Mark your angle in your triangle. That's where t is, my angle. Tangent is opposites over adjacents. Can I solve for the missing side? How? Say that again. How do I solve for the missing side? The Pythagorean theorem. Okay, we just use good old Pythagoras. Take the squares of the sum of the squares of the legs, shove it under a square root. Now, from this information, can I get the secant of t? You bet. Secant is reciprocal of which trig function? Cosine. I like to work with terms and sines and cosines. So we have that cosine of t is what? What is the cosine of t based on our little triangle? Okay, so specifically that's going to be what? Okay, and the secant is just that reciprocal. And folks, now you toss that in. Okay. You have 64 over 3 times the cube of square root of x squared plus 16 over 4 plus a constant. And you're done. Now, if you want to clean that up, 4 cubed is 64, so the 64s drop. So you basically have something that looks like this. But either way, both these answers are equivalent. Both these answers are equivalent. Okay, you can leave it as the one in the top part of the box. That'll be fine. All right, any questions on that one? Any questions on that one? Say that one more time. Or theta or something, yeah. The only reason I didn't choose theta because it'll get like very messy very fast. Like because I'm left-handed, so I can't I can't write neatly. Say that one more time, the integral?
Yes.
Yeah. Okay. So that step there, I just did that to save a bit of time, and that's okay. This yellow step here. Okay, that yellow step there, after we did the variable change, the u substitution in the pink, okay, that would give us the integral of u squared du. Because secant square is now u squared, and tangent t secant t dt, salud. That guy, that's your du earmuffs. Is that okay? Okay. Any other questions? Okay. For the sake of time, I would have done like one more trig sub thing, but I want to get on to like some of the other applications and stuff. So let's actually look at number yeah, let's go ahead and start with 113 here. Okay. It would be really nice if we could have like Cal 2 in these classrooms. So many monitors. That's not my water. All right. Evaluate the integral dx over x times x squared plus 1 by decomposing into partial fractions. Partial fractions is an algebra thing. Okay. It's a tool to help us do the calculus thing. Now let's remember something about partial fractions. Okay, but first this question. How do I add and subtract fractions? Get a common denominator, right? Then we add and subtract across the top. Partial fractions is just doing that backwards. You already have stuff with a common denominator. Now you want to get stuff into its constituent parts. Does that make sense? So what we're going to do first is we're going to look at our integrand, and we're going to break it up into pieces. Now, partial fractions allows us to do stuff with linear factors and irreducible quadratic factors. Irreducible quadratic factors are those that cannot be factored over to real numbers. X squared plus 1, and in fact, any sum of squares cannot be factored over to real numbers. How many of you are familiar with complex numbers? I equals square root of minus 1. Okay, so just to show that, right? If I looked at x squared plus 1 equals 0, and I subtract it over x squared equals minus 1, and I take the square roots on both sides, I get x equals plus minus I. Plus minus square root of minus 1. Now, yeah, I could still factor that, but that's over to complex numbers. Now, the only thing that you have to worry about if you wanted to do it that way is like the arithmetic of I with powers of I squared is equal to minus 1, I cubed is minus I, and so on. We're not going to do that here. That's for, like, if you take complex analysis, sure, you can worry about that later. You can always do linear factors with that. But for irreducible quadratics, I'm going to handle that case first, okay? We're going to break this up into two fractions. For the x squared plus 1 part, at worst, that denominator is linear, at worst. Okay? At worst, that denominator is linear. Now, for the lone x, which is linear, that's x minus 0, at worst, that denominator is a constant a. Okay? So our goal is to find weights A, B, and C such that this relationship holds. Okay, are we good so far on the recipe? In fact, that's the video you should watch. Section 3.4, part 1, the recipe. Understand the recipe to get to the method. That's part 2 of the video. Please watch that and like, comment, subscribe. Well, you can't comment because they turn off comments on the videos, but please like and subscribe. Okay. Where do we go from here? I need to solve for A, B, and C. So I'm going to go ahead and clear fractions. As my pre-calc teacher called it, we're going to fraction bust. That means is we're going to multiply by a common denominator to clear the fractions. And so what we're going to do is on both sides, I'm going to multiply by x times x squared plus 1 on both sides. Do we understand that step? So on the left, we have 1 over x times x squared plus 1 times x squared plus 1. The x stuff vanishes. And so we are left with, we're left with 1. Does everybody see how that works out? We distribute, okay? Algebra step. Let's look at the right-hand side. When I do a over x times x squared plus 1, what thing vanishes? The x vanishes. And so I now have a times x squared plus 1. Now, what about for the second term? What vanishes? Very good. So we have bx plus c times x. Okay? All right. Couple of ways you can take this. You can go ahead and equate coefficients. Okay, multiply everything out and group like powers together and solve for A, B, and C such that stuff happens. Okay, you can do that. Or you can do this so-called cover-up method. Okay, cover-up method allows you to select clever values of x to make something vanish to solve for one of the weights. Okay, I discovered that I also realized this last semester when I was taking my complex analysis class that well, really in complex analysis, all you're really doing is partial fractions half the time. No joke. It's all partial fractions. So we're gonna go ahead and choose clever values of x here. What's a clever value of x here that would make some stuff disappear? 0. If I set x equals 0, well, then take a look at my book. The term on the right, the last term, the bx plus c stuff, vanishes. Because I have 0 times bx plus c. Well, 0 times anything is 0. And so on the left, I am left with 1. And on the right, I am left with a times 0 squared plus 1. Everyone see where that comes from? We're just plugging x on both sides. Okay, if, for example, I had like a... if I had like a 2x minus 3 in the numerator up there, I have a 2x minus 3 on the left-hand side of this thing. I have to plug in x on both sides. Does everyone understand that? Plug in x on both sides, okay? Well, 1 plus 0 squared is 1, so a is equal to 1. And so, folks, we found our first weight. And we have a new piece of information that we can use. All right. Next. Well, can I plug in any clever values, any other clever values to like eliminate anything else? Unless we want to talk about complex numbers, no. I can plug in I and minus I, but we're not going to do that. So instead, we're just going to plug in some other values to give us a system of 2 equations. So if we take, say, x equals 1, or your favorite number, you don't have to choose 1 and minus 1. I just think they're the next easiest numbers. Like, you can plug in 1,000 if you wanted to. In fact, someone plug in 1,000 and like negative 1,000, be my guest. If I set x equals to 1 here, on the left, I still have 1, because the left-hand side is independent of x. And on the right, I have, let's see, so we have a, but I know a already. Can I use that information? Yeah, so a is 1. 1 squared is 1, plus 1 is 2. 2 times 1 is 2. So I have 2. Actually, let me go ahead and just write this out here. So we have 1 times 1 squared plus 1. And then on the next term, we'll have bx plus c times x. That just reduces to b plus c. Everybody see that? Do we have any questions on this step? Okay. So that's one equation. I can't solve it yet because there are two unknowns. So I need to have a second equation. In fact, if we clean this up a little, we get 1 equals 2 plus b plus c. And then I have -1 equals b plus c. Okay, everybody see that? Just manipulation. All right. Now, all right. We're going to plug in another value. I'm going to do this in this light blue color. And it just so happens that -1 is probably the next best one to use. You could use like 2 or 3 or whatever. It doesn't matter. Okay. So when I plug in x equals -1, I get a 1 still on the left because the left-hand side is independent of x. Yeah. On the right, a, which is 1, times -1 squared plus 1. Parentheses, please, y'all. Parentheses, please, okay? Plus, I have x, which is -1, so I'll just put that like this, times bx plus c. X is -1, so I have -b plus c. Okay, you still with me? Yes? Okay, then we go ahead and clean this up. Turns out we'll get a 2 still there for that first thing. Then I'll have minus -b plus c. And I think I did get the wrong expansion in the last one. Okay, that's fine. All right, so I'm going to go ahead and shuffle some stuff over. So I'm going to subtract -2. So I have -1 equals negative b plus c. Oh, no, we're still good. And I'm going to multiply that negative through. So I have b minus c. Okay. I now have two equations and two unknowns. The most basic linear algebra problem that we have. Two linear equations and two unknowns. So let me go ahead and stack those two on top of each other. I have -1 equals b minus c and -1 equals b plus c. I can use my favorite methods for linear equations: substitution, elimination, God forbid, Cramer's rule. Okay. Elimination works well here because I can add these two equations and stuff will vanish. So if I add column-wise, okay, -1 plus -1 is -2. B plus B, or not to be. And -c plus c is 0. We've eliminated c. And so what is b? Okay, now we take that, plug it into either one of the equations. B minus 1 equals -1. That means, oh, sorry. -1 plus c equals -1. That gives us c equals 0. And folks, that's what we got. We have the expansion there in the brackets. And isn't that now that sum easier to integrate? You bet. Both of them are going to be logs. Log of absolute x minus 1/2 log of absolute x squared plus 1 plus a constant. I leave that as an exercise for y'all. Okay. Are there any questions on this partial fraction variance? Yes. Understand the recipe first, and then apply the method, and then the integral follows. I want to set up the expansion for, let's see, 15. I want to set up the expansion, but we're not going to solve that one, okay? I want to move on quickly to improper integrals and some of these applications. Okay, some of these things that we may not have seen in a while. What's different about this one? Right, it's 3 terms now. It's a 3-term expansion because we have repeated linear factors. Folks, that recipe is on your formula sheet. Okay, the recipes are on your formula sheet there. So here's what our breakdown is going to look like. I want to write this thing as a sum of simpler fractions. Okay, whenever you have repeated linear factors, each factor of the repeat, you have to count up the exponents. So because I have x squared, I'm going to have a factor with an x and a factor with an x squared. Excuse me. Okay. And then I have one factor of x minus 1. I have that there. Does that make sense? Okay, whenever we have these repeated factors, we go ahead and count up until we have enough copies. Probably will make a lot more sense when you take differential equations. Okay. Same thing, we clear fractions, apply the method, and the integral is easy. In fact, you can see what the integral will be here anyway. Log of absolute x minus b 1 over x, and then plus c times log absolute x minus 1 plus a constant. But it's your job to find those weights a, b, and c. Okay, so that was just a recipe there. Are we okay with the recipe? Yes? Okay. Kind of halfway there-ish, more than halfway there. Oh boy. All right. In fact, improper integrals I can really do very quickly. Any questions before we move on? Look at 116. Come on. Come on. No. Okay. So I have a question here. If I had just asked you to evaluate, look at this integral. Oh yeah, let's look at that one. If I ask you to do that, how would you do that? Yeah, table works, but in general, it's just called integration by parts, right? Okay. Now what about this one? Say what now? It's still also integration by parts, but what's the only difference now? It's a definite integral. You remember how we handle definite integrals? We find the antiderivative and evaluate on the boundary. Okay, big minus small, top minus bottom, right? The only extra step for an improper integral is that you have this limit process. Nothing changes. You still find an antiderivative. You still evaluate at the boundary. And then you still have this limiting step here. We all see that this is integration by parts. So I can just go ahead and write down the integral. Okay, we know how to do that. Okay, but now remember, we got to phrase this improper integral as follows. Okay, whenever we have an integral where a limit is infinity or minus infinity, or possibly both, that'd be a little delicate if it's both, but you have to pass this to a limits process. You're going to have this as the limit as t approaches infinity of the integral from 0 to t of x e to the minus 3x dx. And we know now know that this, we can use table here, right? Polynomial against exponential, right? Yes. All right. D column, I column. In the D column goes x1, 0. Okay. And in the I column, we get e to the minus 3x. Actually, this is now a good time to test. What's the antiderivative of e to the minus 3x? No. No. You were close. Do we multiply by -3 or do we divide by -3? Divide, okay? If we're differentiating going forwards, we multiply, but when we're integrating, we got to go backwards. And backwards multiplication is division. So we're going to divide by -3 at each step. And then, folks, our usual thing here, tic-tac-toe. So now what we have here is as follows. We have the limit as t approaches infinity of, okay, negative 1/3 x times e to the minus 3x minus 1 over 9 e to the minus 3x. We're going to evaluate this on the boundary between t and 0, plug it in, and take a limit. The only extra step is the limit process. That's it. So probably like another minute or so of computation time. That's it. Yes, you have to do it in that order, inside out, okay? So when we do that, we'll have minus 1/3 t e to the minus 3t minus 1 over 9 e to the minus 3t. And I'll spoil it. If you plug in 0 here, okay, if you plug in 0, you get plus 1/9. I leave that as an exercise. Because in the first one, you get a 0 because it's x times an exponential. E to the 0 is 1. We have 1 over 9 with a minus in front. Minus is a plus. Now we take a limit. The second term is easy. E to the minus 3t, that's the same as 1 over e to the 3t. Computer science majors, remember this. Exponential dominates constants. So if I do one divided by a very, very, very big number, I get a very, very, very small number. This guy goes to 0 in limits. Now for the second term, something similar. Okay, in fact, we'll just show this here. If I have t e to the minus 3t, that's the same as t over e to the 3t. Which one wins, linear or exponential? Exponential wins. Exponential dominates the linear, so this thing goes to 0. And as a consequence, that's also 0. So this integral converges because we got a finite number, and that number is 1 over 9. The only extra step here was the limit process. Okay, so remember this, okay, when you're doing your integral test, if you want to test for convergence of a corresponding infinite series, after you verify that the assumptions hold, okay, what's the only difference for the improper integral? You take a limit, and that's it. Bonus question, speaking of the integral test. Does the corresponding sum related to this converge? Why? Not necessarily that. The integral is convergent, so the sum is convergent. Say that one more time. No, not just because it's less than 1. It's just a number, period. Remember, for the integral test, just in passing, okay, the integral test says that if you can approximate your sum by an integral, given some conditions, and the corresponding improper integral is convergent, no matter what the number is, then the sum is convergent. The integral test. But remember, there are hypotheses to be used for the integral test. All right, any other questions before we go to some geometry real quick? Two 2.1, please. At the very start of the semester, okay, we didn't really learn anything new. I'll be honest. We didn't really learn anything new. FTC was known. U sub was known from Calc 1. Basic integrals were known from Calc 1 at the very end. And now we just needed some applications. The integrals that came out of there, we didn't have many tools to work with. The only technique we had was U sub. And if you notice, if you set up some of these problems incorrectly, you would have to use like parts or something. Now let's take a look here. I want to only write but not evaluate these integrals, okay? And I've drawn the pictures for you so you don't have to think about it. We have a region in the plane bounded by the following curves. Y equals 4x minus x squared, y equals x plus 2, y equals 0, x equals 1, and x equals 2. So what region of the plane is that? Well, we have x equals 1 and x equals 2. Y equals 0 is the x-axis. Oh, I somehow miswrote this. Okay, that's fine. I intended to like use the upper region here, so that's fine. In fact, yeah, let's just use the upper region. So I want to make it interesting for a reason. So we have this region here. If I want to find the area of that little triangle type region, 3 little words. What were they? Area between curves. What were the 3 words that you needed? Top minus bottom. Those are the only 3 words you need for any of these geometry questions. Top minus bottom, or right minus left, but nonetheless, it's still top minus bottom. So the integral for the area, well, it's very simple. The integral from 1 to 2. The thing on the top, that's the line. Thing on the bottom, that's the parabola. That's it. Top minus bottom. Top minus bottom. If you want to think about it, okay? That's a little representative strip of area, and we're sweeping that left to right. The height, the distance, the length of that thing, top minus bottom. Those are the only 3 words you need. Those are the only 3 words you need. Top minus bottom. Intuitive, straightforward. Okay. Say it as you walk out of here. Say it on your drive home. Say it on the rooftop. Say it to your dog. Because it's that key. Let's think about the same region, but instead, we're going to rotate this around x equals 0. Okay, that's part B, by the way. Now I have a question. If I want to rotate that region around the x-axis. Oh, wait, I'm sorry. No, y equals 0. That's right. So that's the x-axis. Okay. Discs or shells? Discs. But Sean, it's actually a washer. Okay, fine, whatever, washer. Every disc is a washer with 0 inner radius. So if I want to find the volume of this thing, rotate it around the x-axis, okay, I think about this. That little strip, I'm going to go ahead and spin it around. And what shape does it make? It makes a circle. And I know how to find the area of a circle, pi r squared. But because it's a washer, because we have the donut hole, okay, so we're going to use discs here. We need pi times the integral from a to b of outside squared minus inside squared. We think about this. We intuit it. Okay, let me go back up to the picture. Salud. Outside radius. Let's draw the picture. Okay, outside radius is that. Again, we think top minus bottom. The thing on the top is x plus 2. On the bottom is 0. So the total distance is x plus 2 minus 0. So whatever, x plus 2. Okay. Then we got to subtract the inside. Parabola minus 0. That's my inside. Same type of integrand. And now you just expand. And now you just expand. Any questions on that? No questions? No. Because what if I sliced it this way with red? What if I sliced it this way? Take a look at the red strip or attempted strip. Still rotating around the x-axis. Discs or shells? Shells. Remember, I mentioned this many times in the videos and in the office hour, okay? Just because we're rotating around the x-axis doesn't necessarily mean we're always using discs. Just because we're going around y doesn't mean we use shells. It depends on how you slice your region. Folks that are taking Calc 3, you'll learn that when you switch the order of integration, you'll get the same thing. If you want to try to do this with shells, be my guest. You got to be a little careful with it. Okay. Any other questions? I want to go ahead and jump on to this one here. Another line and another parabola. The region that we're talking about here is that. Now, of course, area is easy, top minus bottom, right? We know how to do that. But of course, remember, we have to figure out the intersection points. We set the two things equal to each other. Solve the corresponding system of equations. We get our limits of integration. Now, you can do this in X, you can do this in Y. They're both relatively straightforward. I already gave them as Y as functions of X, so you might as well integrate in X. Now, we're going to rotate this thing about round the line X equals 4. Draw the arrow. Now draw your little representative strip. And now, folks, I ask the important question. Discs or shells? Shells. How do we remember? Shells are parallel. Shells are parallel. If I'm slicing parallel to my axis of rotation, I'm using shells. We're using shells. And how do we think about shells? What's the area of this piece of paper? How do I find the area of this piece of paper? Yeah, this is a rectangle, right? Area of a rectangle is length times width. But the instant I glue these two ends together and turn it into a cylinder, have I changed a certain lateral surface area? No. It's just now that the base has been rolled up into a circle. 2 pi RH. Sound familiar? We need the shell radius and the shell height. Now, the good news is the shell height is easy. Why? 3 little words. Top minus bottom. Yeah, say it to your dog, right? Just go out into the street, grab someone by the lapel, say top minus bottom. Well, probably don't do that because, especially not on Sunday, because, well, anyway, that's a Cinco de Mayo joke. Okay. So the shell radius, the shell height rather. Okay, the height here is just, let's see here. It's going to be the parabola minus the line. And now let's think about the shell radius, okay? Think about the shell radius, okay? The shell radius is the distance from the axis of rotation to a representative strip. Now, I said something earlier that the shell method uses both the top minus bottom and right minus left principles. We already used the top minus bottom principle, so we should be using the right minus left principle, right? The thing on the right, that's fixed. That's always at X equals 4. And the thing on the left is allowed to vary. That little blue strip sweeps left and right. That's our variable X there. And so how do we think about the integral? The volume here, 2 pi times the integral from 0 to 4, shell radius, times shell height. Now, of course, to evaluate this, you got to be careful with the multiplications and everything, but it all just works out. It's still basically power law. Do we see how to set that up? It is your choice. It is your choice. Same with the area between curves. You can slice it either way because, again, by Fubini's theorem, because everything works out nice, if I switch the order of integration, everything works out to be the same because everything is nice here. It is just your choice. It's whichever feels more convenient to you. There was a question here. Yeah, so for radius, how to find the radius? Again, you use So shell height, use either one of the top minus bottom or right minus left principles, depending on how you slice. And then for the radius, you use the other one that you didn't use. Say that again. We use right minus left here. Because in the pink there, okay, here, well, it's now black, but in that distance is the radius, okay? It is the distance from my axis of rotation to any representative strip. And then when I wrap it around and glue it, which I should have gone ahead and like drawn the shell. Okay. The shell radius is just the axis of rotation minus the representative strip. Yes. Next step B for this multiplication, it just ends up being power rule UN. So use the F word, not that one, the other one, the one for corn and tacos. Okay. Use that F word to multiply this out to get like 8 square root x minus plus x squared plus some junk, and it's just power rule. Yes, question. Say that again. Yes, if you slice it the other direction, that's important. So if you instead slice the other way, these are good questions. I like these questions. So if you slice the other way, actually, I want to do this in purple. So if I slice this way, so instead I slice this way, this way, this way. Okay, if I slice horizontally, okay, now I'm slicing orthogonal, sorry, perpendicular to the axis of rotation. Did I just break this? I really hope I didn't. Folks, it's the end of the semester. I can kind of feel the throttling here as well. This thing. All right. So if I slice the other direction, I can use washers. Okay. But I have to, since I'm integrating in with respect to the other variable, I have to make sure I get functions of y. And then I do outside squared minus inside squared. That's the harder part there. Okay. And same reasoning for the radius there. It's out distance from the outer part to the axis of rotation and similar. Of course, the integrals will still work out to be the same by Fubini's theorem. It's just your choice. Yeah, you have to write in terms of the other variable. So we have x equals y already. That's fine. But then for the other one, to solve for x there, I get x equals y squared over 4. Yes, but the thing is, for that one, sometimes you may not get a local inverse. You have to like consider it in cases, and you may have to like split up the integral into multiple pieces, which is a pain in the butt. That was just based on again, that is just based on the way that I sliced. If I elect to slice parallel to the axis of rotation, then I'm using shells. Why? Because shells are parallel. If I elect to slice perpendicular, then I'm using discs. Nowhere in here does it say use this method, use that method. You have to determine that reason. That's again that logic and reasoning. Draw the picture. So you have to take your paper and just fold it, and you'll see, right? Yes. Because the way that I slice it here, because that's a very good question, actually. So the line x equals 4, that's a vertical line. And if I want to slice parallel, my slices need to be in the same orientation. This line is parallel to that line. Okay. X equals whatever, some arbitrary x. Correct. Slice horizontally, yes. Yes. Again, for the these questions, it's up to you how to decide to slice, whichever one is. Again, some of these may be easier out of convenience one way or the other. Here, because we already have functions of x, you may as well just use functions of x. That's a very good question. That's an excellent question.
Do one where we're gonna find the intersection.
That's actually this one right here. Well, assume that like you don't have the grid lines. Never trust the picture. A picture is worth 1,000 words, but is also worth 1,000 lies. So how do you do that? How do you find the intersection points? You take your two things. Well, your two things basically give you a system of equations. You have y equals x, y equals 2 square root x. They're both set equal to y, so we're going to equate them. I can square both sides to eliminate the square root. And then I solve this equation. Okay, it's a quadratic, so we just use the other f word, and then we get two solutions, and then we get the corresponding x and y values.
The better challenge than some of them, yeah, or some challenge that-
Well, so sometimes you can, but like that, like you can't just write down an equation and like hope for an analytic solution. That's a whole another can of worms. But like again, assuming in an exam setting you get ones that are easily doable by factoring, easy cancellation, or just using nice inverse functions. Like a pop quiz, what's the inverse function of log x? What's the inverse function of log x? E to the x. Okay, so it is up to you to remember how to solve these basic equations that we solve from algebra. Okay, I know some people are packing up. I just want to like kind of touch real quick on series, okay? Although it is still kind of fresh in your minds a little bit. I won't solve some of these. I'll put up both recordings. But if we take, and also the physical applications, you can rewatch the corresponding videos for that. Well, again, timing. We had some good questions here. So I would rather answer very good questions than try to rush through everything. Okay. So let's talk about like say, for example, this one, we're talking about intervals of convergence. We have a theorem that says that a power series will always converge if it does on an open interval. We are guaranteed open interval. We don't necessarily know about the boundary. So to get the interval of convergence, I need to first think about this with the ratio test. Okay. Most powerful tests out there. We're going to use the ratio test. All right. I can probably really quickly write this one down. So we have the limits as n goes to infinity of, so take the n stuff, everything there depends on n. So we have -1 to the n plus 1 times n plus 1 squared, x to the n plus 1 over 2 to the n plus 1 times, now we multiply by the reciprocal of the original stuff. Okay, 2 to the n, all this. And now we evaluate this limit. Now remember, this limit depends only on n. So if I have a lone x in there, can I just pull it out of the limit? Yes, because take a look there. I have x to the n plus 1 divided by x to the n. That's just an x. And that gets pulled out of the limit with an absolute value. So if we think about this one, after we do some cancellations, okay, -1. The negative ones don't really care because absolute value of -1 is 1. Okay, we'll get something like n plus 1 squared over n squared times, I think we get an x over 2 left over. Okay, if we do the simplification. Okay, and I will have all solutions to all 35 problems posted hopefully by Sunday. Okay. When we do stuff here, we'll get like absolute x equals a thing. Well, absolute x over 2, because I can pull the 2 out of it as well. And the square stuff, that goes to 1 in limits. Don't use L'Hopital's rule for that, okay? Easier. It's equal heavy. Divide out the leading coefficients. Okay? So we have that this is the limits. And I want this thing to be less than 1 because the affirmative case of the ratio test says that if the limit that comes out of the ratio test is less than 1, we get convergence. So in order to satisfy convergence, I need that inequality to be satisfied. we solve our absolute value inequality. Okay, remember that from algebra, right? That absolute value of x less than k means that x is between k and minus k. Okay? That's a joke. Anyway. Okay, so we solve this inequality. We get that absolute x is less than 2. So I know for sure this thing converges on this interval. But the problem is I have to plug in the endpoints. I have to plug in the endpoints to check if I have convergence on the boundary. So I would have to plug in x equals 2, x equals -2. I'll spoil it for you. I don't think either one converges. I know for x equals 2 it doesn't. Certainly doesn't for x equals 2. X equals -2. Yeah. Yeah, so it fails on the boundary. You can verify that as an exercise. So I'll say verify that the above diverges on the boundary. Okay. Any questions? Yes, because the squares there, okay. Yeah, they'll go to 1. You have n squared plus garbage over n squared. So basically it's something O of n squared over something O of n squared is still basically a constant. Question? Not always. Not always. No. You have to actually verify it and plug in the number. So for example, if I plug in x equals 2 there, it certainly fails. So I have 2 to the n over 2 to the n, those drop. I have -1 to the n times n squared. That diverges because the terms get large. Yes.
Especially if it says where does it converges. If it doesn't converge, then we need to say where is it divergence.
No. So there's a dichotomy. There's no question mark here. Either the sum converges at a point or does not converge at a point. So the theorem that we are basically using says that if it converges inside an open interval, it must diverge outside of that interval. Now, the thing is here, like I said, we have to check the boundary and it fails. That's an exercise. Okay. But just because we have an alternating series doesn't mean we get convergence on the boundary. We have to verify that. There are some very special cases that we have to look at for that. All right. Okay, we're already like about 10 minutes over. I really don't want to keep you guys here any longer than you need to. Like I said, everything is available. Okay, I'll have these recordings available tonight and I'll get you solutions. Folks, thank you very much for being my last real assignment as a graduate TA here.
Video.
Folks, thank you very much.